Video is on 8.3, logarithms. Something you never really learned about before. Let's start with some basics. 2 to the x equals 8. Then what is x equal? 2 to the x equals 8, then x must be 3, because 2 to the third equals 8. And if 2 to the x equals 16, then x must be 4, because 2 to the fourth is 16. But what if 2 to the x equals 12? There's some number we could plug in for x here that would make 2 to the x equal 12. We know it's got to be bigger than 3, but smaller than 4, because 2 to the third was 8 and 2 to the fourth was 16. So for 2 to the x to be 12, excuse me, x has to be between 3 and 4, but what is it exactly? We start guessing and checking and trying things. Over here, we made the graph of the function y equals 2 to the x. And if we look at this graph, remember, this shows all of our possible solutions to the equation y equals 2 to the x. So the y value equals 12 here. This is a y value of 12. If the y value is 12, the x value looks to be a little bit bigger than 3.5. So it's probably 2 to the 3.5-ish. We can check that in our calculator and see what happens if I do 2 to the 3.5. And then it's close to 12, but I've actually got to go bigger. 2 to the 3.6. No, that's too big all of a sudden, so I'm between 3.5 and 3.6. This is not a great way to solve a problem like this. Solving a problem like 2 to the x equals 12 by guess and check is not ideal. And in fact, a more worthwhile problem is a problem like this. If you have $20,000, meaning 5.4% interest compounded monthly, how long until you have $100,000? I've avoided asking you questions like this so far because we don't actually know how to answer them. The equation for this would set up like so. 1,000,000 equals 20,000 times all that stuff to the 12x. But the fact that there's an x in that power, the fact that the exponent has a variable in it, means this can't be solved in the ways that we have tried to solve things before. We need a new method of solving, a new tool, and that tool is called the logarithm. The logarithm is a tool we use to solve exponential equations. There's two things you'll hear me say very often. Logs are exponents, and that logs or logarithms, same thing, are inverses of exponents. Remember, an inverse is how we undo things. So an exponent is undone by a log, and a log is undone by an exponent. Remembering the equals sign literally means the word is, or are, or same. Equal sign means those things. And I'm going to kind of just start playing with logs in a way to introduce them. And I'm not going to try to explain what a log is yet. I think that'll take some understanding and some familiarity first. So first we'll just convert. In exponent form, I know that 3 to the fourth is 3, 9, 27, 81. 3 to the fourth is 81. Remember how I said that log is the exponent? Logs are exponents. Here the exponent is 4. Well, in logarithmic form, I write log base 3 of 81 equals 4. Now these two things are expressing the same relationship. 3 to the fourth is 81. The exponent over here was 4. Base 3 of 81. So when I say logs are exponent, this was the exponent. The whole entire log, the log, is the exponent 4. That's exponent 4 over here. I'll do some more examples. 5 squared equals 25. That's an exponent form. So in log form, I would say log base 5 of 25 equals 2. I often like to put this stuff in parentheses. You don't have to. The book doesn't, but I find that helpful. You'll kind of see me do it both ways. Over here, this is called the base. 5 was the base of that exponent, and so 5 is also the base of this logarithm. That won't ever change. The base of the exponent and the base of the logarithm are the same. 2, excuse me, I apologize. 2 to the 6, 2, 4, 8, 16, 32, 64. 2 to the 6 is 64. Try and look ahead of me if you want to pause now. Log base 2 of 64 is 6. I'll go in the other direction now. I start with the log form. I have log base 10 of 1,000 equals 3. Well, I call this the circle thing. When I go from log form to exponent form, I do the circle thing. 10 to the third is 1,000. 10 to the third is 1,000. There's the exponent form of that previous log form. Some more. Log base 8 of 64 equals 2. So if I do the circle thing, 8 squared is 64. And log base 2 of 128. I believe that's going to be 7. Yes. 2 to the 7th is 128. Okay, so logarithm is another way of writing an exponential form that kind of rearranges all these three numbers. The base, the power, and the result. I call this number here the result. There's probably an actual mathy term for it, that's what I call it. So this is the base, this is the power, and this right here is the result. Okay, we can evaluate logs. Whenever you see something like this just stands for some number. It's not written like a number, it's written like a weird function. Log base 3 of 9 is really a function. But it's also some number, it represents something. So the question is, 3 to what power equals 9? Well, 2. Log base 3 of 9 is just a number, 2. 2 to what power equals 16? So I'm really asking the question, 2 to what power equals 16? Well, that must be 4. 2 to the 4th is 16. So log base 2 of 16 is really 4. 2 to what power is 1/16? So there's like an x there. 2 to what power is 1 over 16? Well, I know that 2 to the 4th is 16 from my last problem. So 2 to the negative 4 must be a 16th. So this must equal negative 4. 1/4, there should be a number here, excuse me, this is written wrong. Log base 1/4 of 64 equals. So that should be written. 1/4 to what power equals 64? Well, negative 3. 1/4 to the negative third is really 4 to the positive third, which is 64. It's evaluating logs, just seeing what they equal. Keep going. Remember, sometimes it's helpful to think about this like it's a function, like instead of having f of 10, where f is some random function, we have a special function called log now, log of 10. This is saying the log of 10. If you ever have a log with no base written, where there's no number down here, we make it base 10. We call it the common log. So log base 10 of 10 is 1, because 10 to the first is 10. And log base 10 of 10,000 is 4, because 10 to the 4th is 10,000. So here the base is 10, so it equals 2, because 10 squared is 100. And here the base is 10, so it's going to be negative 1, 2, 3, 4. It's negative 4, because 10 to the negative 4 is 1 over a 1 with 4 zeros. You ever see log without a base written, that means it's base 10. Otherwise, the base has to be written. You know, log base 3 of 9 equals 2. And now we're going to graph them. Now, graphing is just evaluating over and over and over. Once you get comfortable doing stuff like this and doing stuff like this, graphing is just evaluating over and over. This is really saying 2 to what power equals x. That's really what this is saying. So what I want to do is be smarter than the problem and plug in numbers for x. I don't know if you can read it. Plug in numbers for x that give me clean numbers for y. What that means is I want this value here, this x value here, to be powers of the base, which in this case is 2. Powers of 2. So powers of 2 are like 2 to the negative 1, 2 to the 0, 2 to the first, 2 to the second, 2 to the third, a half, 1, 2, 4, 8. So I'm going to plug those numbers in for x. So that'll be my x column. I'm going to plug in a half, 1, 2, 4, 8. I won't plug in 16 because that gets too big. But I do think I'll move that down actually. I'll put like this. Put that there. So I can also plug in a quarter. A quarter is the power of 2. Well, let's do this one first. Let's talk through this one. What I'm really going to graph here is, make more room, I'll just make this work. Y equals log base 2 of 1. So the question is, 2 to what power equals 1? 2 to the 0 power equals 1, so the y value must be 0. This is the point 1, 0. So now we'll do this one. I'm really doing y equals log base 2 of 2. And the question is 2 to what power is 2? Well, obviously the y value must be 1. This is the point 2, 1. 2 to what power equals 4? 2. 2 to what power equals 8? 3. 2 to the third is 8, so the point 4, 2, 8, 3. And I could do the point 16, 4 if I really wanted to, and 32, 5, but you get the idea hopefully at this point. So now we go negative. 2 to what power equals a half? Well, that's negative 1. And 2 to what power equals a fourth? That's negative 2. Here's the point 1 half, here's the point 1 fourth, there'd be an 8th down here, and a 16th down here, and a 32nd. I can just keep on going like so in that fashion. This graph has a vertical asymptote. Our exponentials had horizontal asymptotes. This one has a vertical asymptote. It's the line x equals 0. In fact, think about how y equals 2 to the x looks. I'm going to erase all this now, so if you want to go back and pause it and look at it. If we think about graphing y equals 2 to the x, well, that has the point 0, 1, 1, 2, 2, 4, 3, 8, and then negative 1 half, negative 2 1/4, and it goes like this. And those are reflections over the line y equals x. It's a reflection over this line. And if you remember from our last chapter, anything that's reflected over the line y equals x is really an inverse. These are inverses of each other. The inverse of y equals 2x is y equals log base 2 of x, and the inverse of y equals log base 2 of x is y equals 2x, because this table would be negative 2, negative 1, 0, 1, 2, a quarter, a half, 1, 2, 4, has just switched x and y points. We just switched the values of x and y. So an exponential function has a horizontal asymptote right here. A logarithmic function has a vertical asymptote, and the reflections of the line y equals x. So when you graph, I'll come back to this in a second. When you graph y equals log base 2 of x, if you would rather, you could take that and convert it by doing your circle thing, and instead, I wrote that all pretty poorly, the circle thing, 2 to the y equals x. Instead, just graph 2 to the y equals x and plug things in for y. And here's what that says over there. I can plug in numbers like negative 2, negative 1, 0, 1, 2. And 2 to the negative 2 is a quarter, and then a half, and then 1, and then 2, and then 4. Our logarithms follow the same pattern that everything else does, where the h moves things left to right, the k moves things up and down, the a is your dilation, and b is your base. B cannot be negative, and if it's less than 1, it has decay. If it's greater than 1, we have growth. But the important thing to understand is the asymptote is now the line x equals h, not the line y equals k. With our exponential graphs, it was y equals k, but now with logarithmics, the asymptote is x equals h. So again, I understand that you still might not feel like you get what a logarithm is, and we'll get there. But first, you have to just kind of get familiar with how to even work with it. Here's how, if I'm going to make this problem uglier, I'm going to make this problem like this. Here's how I recommend you graph a problem like this for now. I'll eventually show you and let you do this on your graphic calculator. But I'm going to start with doing it by hand. I'm just going to grab this. I'm just going to look at the graph of y equals log base 1/3 of x. I'm not going to worry about the plus 1 or the times 2. I'm going to think, okay, what numbers should I plug in for x? I'll make a little table over here. I want to plug in powers of 1/3. Because that's my base. My base is a third, so I plug in powers of 1/3. Well, 1/3 to the 0 is 1. That's what I plug in for x. 1/3 to the first is a third. 1/3 to the second is a ninth. 1/3 to the -1 is 3. 1/3 to the -2 is 9. So those are powers of -2, -1, 0, 1, 2. So I'm going to evaluate this first. If I do log base 1/3 of 9, I know I'm going to get out -2. That's the power that got me there in the first place. I'm just doing and undoing things with inverses. If I do log base 1/3 of 3, I get out 1. And log base 1/3 of 1, I get out 0. So that should be -1. And so these are my y columns for this function right here. So that function then gets multiplied by 2 and added 1 to it. So I'm actually going to take -2 and do it times 2 plus 1, and that's -3. I take -1, do it times 2 plus 1, and that's -1. Do 0 times 2 plus 1, and that's 1, and I'll go 3, and then I'll go 5. So my table looks like this. I'll pick a finer point in the graph this. But I have the point 9, -3, which is here, 3, -1, which is here, 1, 1, which is here, 1/3, 3, which is here, and 1/9, 5, which is here. And this has a vertical asymptote. The graph's like this. The asymptote is at the line x equals 0. I did do domain and range last time. The domain now is always going to be the set of all numbers x such that x is greater than 0. The domain is now based on the asymptote. The range is going to be all real numbers. So that's pretty nice. Domain is going to be based on the asymptote, range is all real numbers. I will make another video of me doing lots of graphing examples later, but I think this is a good start.